Hello friends, welcome to Thermo. We're about wrapping up our Thermo sequence if you're watching these videos in order, and we are doing second law and Carnot engine for this one. Pretty an extensive topic. I'll try to get through it relatively quickly here, but thoroughly. So buckle up. So the second law of thermodynamics, which is one of our fundamental principles for this course, has multiple statements. There's the Kelvin-Planck statement, the Clausius statement, there's different statements. We're going to focus on two statements for this one. So statement one is that no power cycle, so like the Rankine cycle, can achieve 100% efficiency. Which makes sense. I mean, we look at our first law of thermo, and we can determine that we definitely can't get more than 100%, but we have to start thinking about why we can't get exactly 100%. Why does it always have to be at least 99%? So this is basically just telling us that this thermal efficiency that we've been finding and paying attention to cannot be greater than or equal to 100%. So why is that? Well, it could be friction is an obvious one. Another one could be that you would have to have heat transfer with no temperature difference. We're going to look at a TS diagram to show that, but I wrote that wrong, with no delta T. So we'll look at that. But those are the two main reasons why we can't achieve 100% efficiency. So the second statement, so a power cycle, which can also be known as a heat engine, cannot accept heat from and reject heat to a single temperature reservoir. So that just backs up the first statement as well, that if you think about why this is we can't achieve 100%, a power cycle can't accept heat and reject heat to the same temperature reservoir. That would be heat transfer with no delta T. So those two statements are going to guide what we talk about today with heat transfer and specifically Carnot engines. So if we look at a TS diagram here, we know that typically we have some sort of reservoir up here. We're going to say that this is some sort of fire. So think about if we're trying to run a boiler, because remember across this top part when we come across our cycle is a boiler. We're receiving Q from that fire source. So this would be Q in. And then when we are trying to cool something using our condenser, we're down here at some sort of temperature. And this is going to be the temperature of the cooling water. And that is going to draw heat to it in our Q out. Excuse me. So we know that in between these two lines, we do area under the curve here, and actually area between the two lines. This is going to be our net heat transfer. We're just going to put HX there. So net heat transfer, net work. You could also net work depending on what we're looking at here. But that's between the two lines, we're going to get that net work there. But if we were to have some sort of single reservoir here, so we're going to say that it would have to be somewhere in the middle here, something like this, going across here, to have a reservoir that both we could draw heat from, but we could also send heat to, you would have to be at the same pressure for both, which would then cause other problems because when we think about work and think about what happens with that pressure difference, this is going to cause problems because we don't have any area between those two lines because no heat transfer can happen because there's no delta X. So, or no delta T, sorry, not delta X. There's no delta T, there's no difference in temperature. So you can think about this as like if you were to have a book and you were going to determine its potential energy. If the book is already on the floor, there's no potential energy. But if the book is on a table and has the potential to fall off, there is a potential energy. So you have to think that there has to be some sort of difference or gap that we're trying to overcome or take advantage of to be able to actually create this net work or this net heat transfer. We have to have a difference in energy between those two reservoirs that we are working with, either for our boiler being our hot reservoir, our condenser being our cooling water or cool reservoir. So transferring that to a Carnot engine, a Carnot engine is simply the best power cycle possible without violating the second law. So basically in this, we are just going to maximize our temperature difference to be able to achieve our best efficiency without violation of the second law. So we're going to go back over here. Let's draw on, we're going to have a T fire again here. So this is our T fire, which in this case, let's say that it is 2460 Rankine. And then let's also put on our cooling. So this is our T of the cooling water, and let's call that 500 Rankine. And we know that if we were to have these two pressure lines here, we would get this amount of network somewhere in the center. But if we're doing a Carnot engine, we are going to maximize the area between these two lines. So our area is going to be, let me use a color that'll stand out here. We're going to draw our points here where it intersects, about right there. So this is going to be our area between the two lines. So you can see that based on the temperature reservoirs that we have maximized the amount of network or net heat transfer that can happen based on these circumstances. So since we maximize this heat transfer process, let's now figure out, well, just how efficient are we if we maximize these temperatures? And that's something that we can then pull the efficiency equation. So the efficiency, oh boy, Carnot, I'm struggling spelling today. So the eta of Carnot is equal to T of our source, which is going to be our hot that we're drawing heat from for our boiler, times delta S, minus T of our sink, and we can think of that as what we're rejecting heat to, which is going to be our cooling water, times delta S, over T source delta S. And you can see in this case, this derivation we're not going to go through today. We can get to it based on what we've learned, but that is not worth our time spending here. We can go over that if you're interested, or you can do some researching on your own to see where that derivation comes from. But we can see from this chart of our Carnot engine, all the delta S's are going to be the same when we're trying to find that maximized heat transfer. So if we were to then write this without the delta S's, this efficiency of the Carnot is equal to just our T source, or our hot fire, whatever, minus T sink, which is our cooling temperature, over T source. And we're going to make sure to use absolute temperatures here, just like we did when we were finding area under the curve before. So in this example, if we do it with these numbers that I put here, we can think N Carnot, ooh, this pen is working really good right now, is equal to 2460 Rankine minus 500 Rankine over 2460 Rankine. And remember that all our efficiency is telling us is how much of a heat difference, so our difference between our source and our sink, can be converted into some sort of useful work. So that's what our efficiency is telling us. You'll also hear of something called coefficient of performance. Maybe you've already heard of it. Maybe we've already done an example problem, depending on what order these videos end up in. But that tells us the amount of heat transfer for the amount of power used. So it's the inverse of efficiency. So we're looking at a few different, or two different perspectives there of what we're trying to maximize. Here we're trying to maximize this temperature difference and see how much of that can actually be converted into useful work. So if we are to do this, we get a value of, actually, I'm going to put this down here, is equal to 79.7%. Obviously, this is a times 100 to be able to get a percent. So if we maximize our temperatures here between our source and our sink and get all of the network possible between these, so basically we're taking our boiler up to the temperature exactly of the fire, and we're taking our cooling water exactly to the exact temperature of the cooling water to get that maximum amount of area, we're still only running 79.7% efficiency. And thinking about ranking or giving like a hierarchy of what we know about thermal efficiencies. Let me grab a different color again here to not confuse this, to just finish this out. We know that our N thermal equal to 100% is impossible. And then we know that our N thermal equal to 79.7% is our Carnot, which is still just not achievable because we're not violating the second law, but we just can't maximize in that way. If you think about heating up something and trying to get it to the source temperature, it's just not going to be possible. So great. And it's frictionless. It doesn't have those losses that we account for, but it's still not achievable. So I'm just going to put NA, not achievable. So then we come down here and we have what we've learned as the ideal, which we could say here maybe I should put about equal to 60%. So this would be our ideal no friction. And then we have a step down from that where we look at about, I'm standing behind this and you probably can't see it too well. We're going to call this is about 55%, and we're going to call it a real modified. And this is going to be in an advanced thermo class. You'd be able to do this. We're not going to do it in this class. And then there's the real that we've calculated for this course, which is about 45%, maybe, say. So this gives us, that's what we've done in this class for real. All right, so this gives you a hierarchy. This gives you an idea of, depending on what you do with friction and your losses, what your thermal efficiencies may look like in this specific situation. Make sure to not think that 79.7 is the highest that you can ever achieve, because that's not true. That's just the Carnot efficiency based on these temperatures. If you changed these temperatures, this is going to look different. So don't come back saying, well, Carnot efficiency is 79.7%. No, it's not. It's depending on the temperature that we have and that temperature difference. You can see how that would change depending on what those values are. So a Carnot engine is the best power cycle possible without violating the second law. And dependent on these temperatures that we have, we can maximize that heat efficiency. But again, it's great, but it's not achievable. It's not violating the second law, but we just still can't achieve it. So that gives you the overall view of the second law, what our second law of thermodynamics tells us, those two statements, as well as how we, I'm going to say overcome that with the Carnot, though it's still not achievable. This just gives us our ideal, our more realistic ideal without violating the second law of thermodynamics. So there you go. If you have questions, come back with them. This was a lot, so there's a lot to process. So definitely write down your questions and let's answer them in our learning conversation.